Good evening and welcome everybody. This is Obi-Wan Pez for and Simplex Pachinko. We are going to be doing some differential equations tonight. I know Zach said he is out and unable to make it tonight. However, we may have somebody else coming in and we'll see what else is going on as we get through some of our material. So, if nobody else does come in, that's perfectly fine. Can run class as usual, get through the prompts that I have, and then we can maybe work on other mathy type stuff if time permits, or else, I don't know, I'm feeling pretty tired, so we might just have an early night or something. I don't know. Figure it out. Alright. So. Coming from last class. We had discussed that last time we were looking at the most basic differential equation systems, which we had used, and we were curious what kinds of major categories these systems fell into. So, from last time we had... Right. You have got to be kidding me. Really? That's awesome. Nope, there we go. Okay, cool. It is working. Phew. Thought for a second there it was going to fail me.
Hello.
Hey, Snooky. Sorry about that. I started early.
Oh, what's that?
I accidentally started early.
Ah, well. Hello.
How are you doing?
I'm doing well. How are you?
Hanging in there. I apparently need to work on my timing. Anybody who has not hung out with our friend Ian Stucky, they are on their own Twitch channel and Discord given below in the chat, and they also do mathematics streaming, mathematics teaching, and talking about other cool stuff. Do you have anything you'd like to plug?
No, I don't think so. Stay tuned for the announcement of season 2, but it's I'm going on my last travel tomorrow, so I'm excited to get back to a stable place that I can like stream consistently again.
Yeah.
Yeah. You know all about that.
Yep. Yeah, my fortunately our moving days are done for the next 3 years. I shouldn't say that. I'm just gonna jinx it. But you know, as long as the rental department is perfectly happy to have us, and the owners want a stable income and don't want to sell off the house or whatever,
Right?
I think we're gonna be in the studio for a while. I like it. Yeah. Also, my parents are in town, so this has been a fun couple of days. So, but they've been leaving us around when the kids start getting ready for bed, which is usually 8-ish. So perfect timing for getting ready for stream and whatnot.
Yeah.
And once again, apologies to everybody for just completely starting early. So I'm sure that never happens in real life.
It doesn't look like it's that early.
No, but I did the intro stuff, so.
Nice.
Yep, and I think we've done our last vacation for the summer, so we will be streaming at regular times apart from all this. Yay, sensation! Yeah, 2100. I think I started at like 2058 or something, and actually doing my starting to introduce stream and whatnot, which, you know, maybe nobody cares that much, but at the same time it was kind of like, well, I'm supposed to start at 9 anyway. So we were talking last class about the most basic differential equation systems, and we had 3 of the major categories that we had talked about for, again, the most basic type stuff. We said that our eigenvalues were going to belong to the real numbers. At least, again, this is the easiest way to do things. And then we had 3 different classifications, 3 different types of behaviors that our system could have based on the values of the eigenvalues. And Stuki, do you want to play the matching game?
Okay. So we have for 2x2 systems, we're gonna have is this where am I going the right direction? 2x2 systems, we're gonna have the eigenvalues can be real and distinct, real and the same. Okay, so there's one eigenvalue, or complex conjugate pairs.
Right, and let's go with real and distinct first.
Okay.
So we had the 3 major behaviors, which were, we were going to see sources, sinks, and saddle points.
Gotcha.
And what kind of real distinct eigenvalues do we need to get those things?
I see. So the sources, probably both eigenvalues are positive. Sinks, they're both negative. Yeah, that sounds right. And saddle is one of each.
Yeah, so we'll do something like this. You know what? Let's just do 1 and 2, because even though we could have many multiple different kinds, we'll just say that for the sake of argument, we've got 2, and they're on either side of 0. Okay. And to get back to your other point, right, we also noted, although we didn't see any systems yet with those behaviors, that there were 2 other behaviors for those systems, because our characteristic equation which is a polynomial on our variable lambda, had 3 types of solutions. Always with the creepy music. Trying to tell me something. Stalking the prey. piano cocktail. That sounds more appropriate.
To turn it on for just a second.
Alright, so 1 was that they could be real and distinct. 2 was we could have a repeated root. And real. And the third was that we had complex conjugates. Okay, and with that, we said that repeated roots being real, we had 2 behaviors that we could get out of that. Again, we just discussed it, we didn't really see it, but we'll see an example of this a bit later.
All right.
All right. Repeated roots could either be positive or negative. Again, we're not going to have any zeros. That just makes everything trivial solutions.
Hi, chat.
Apologies.
Still on mic, off camera, but on mic.
I was on mic?
I heard you say that.
Heard me say what?
I don't know. Whatever you said, I didn't hear. Listen to what words you said. I just noticed that you were there.
Okay. Anyway, yeah. So the repeated roots, right, could have either positive or negative values. We can't have zeros because that just makes trivial solutions. I was hoping that's where it cut off.
Yeah.
Okay, good. Daughter came in to say goodnight, so. Right. And when lambda is either less than or greater than 0, what kinds of behaviors do we get there?
I'm guessing those would be sources and sinks.
Yep. So just the same as above with the pure real examples. The only difference is that we're going to have some alternate weirdness that's going on that's not going to be entirely based on the one eigenvalue that we have, or eigenvector that we have. All right, and again, we'll see why that is in a little bit. Okay, and complex conjugates, we said that here we're going to have real parts, which we're going to have a real and a complex part, natural or real and imaginary part. So something like a plus bi and a minus bi. And we said here there's going to be 2 different behaviors again. And what's this based on?
Probably the sign of the real part.
Yeah. Since the complex part, or the imaginary part, is going to both be positive and negative, right? We can't really do a whole lot with it. Can't make a whole lot of inference as to what's going on. However, with the A part, we say if our A is less than 0, or if our A is greater than 0, we're going to have, again, 2 behaviors. It's going to, again, do the exact same things, its sources and sinks, just like we did for the other 2. The only difference is that it's going to do what kind of behavior?
It's also going to have a rotation.
Yeah. So oftentimes we end up calling this a spiral sink and a spiral source. Just to add an adjective on to give it a little more description. Alrighty. And solutions, eigenvectors, and exponential terms formed what kind of structure? So like what could we make from those solution parts to get the overall solution?
So I'm not quite sure what
That's
you're
okay.
hoping for here, but when I think about solutions to systems, I think about pairing each eigenvector with an exponential of the corresponding eigenvalue, and then taking linear combinations of those products.
Yep. So we got all the important pieces. So I was talking about here how we are going to have C1 and C2 as our eigenvectors. We are going to have e to the lambda 1 and 2 respectively times t. And then the actual question I was asking was the last part you said, we need a linear combination of those things. Okay, and why do we say a linear combination of those things?
So we can, the system is linear, and so if we sort of trace back through, this linear combination, then we can see that that's going to be a solution when the two component parts are solutions.
Right, so the differential equation is linear in x, like the x vector, which is our dependent variable. Or a system of dependent variables, but nonetheless, that's all the same there. So what we're going to see because of that is that we have a linear combination of all of the exponential functions that we get on the outside of it, with again these eigenvectors, which part 2 7, yes. So our two eigenvectors from what we had before are going to form what mathematical structure or what relationship do they have to each other, which is using a term from linear algebra.
Yeah, so they are linearly independent as elements of R2 or R2T.
I'm using two different tenses. Right, these things need to be linearly independent from each other, so why?
I guess I think about it in sort of a similar way that I think about systems of linear non-differential equations, where I am expecting. No, that's not really what I mean. Let me try that analogy again. If our system was a 1-by-1 system, I would know that there's supposed to be a constant coming from the constant integration, right? Plus c shows up somewhere, and then eventually that filters down into into a constant multiple of the solution. And I guess the analogy there is like, if you have these two, they're not linearly independent. I guess this would correspond in the 1-by-1 case to like you have the zero solution, right? It's just somehow there's not enough going on.
And I will totally take there's not enough going on. Alright, so let's suppose that we have C1 here. And if all we want is a linear combination of the only eigenvector that we have, then where are our solutions going to be?
They're going to lie right. They're going to lie on that line, on that line spanned by the eigenvector.
Right. So what we see is that we end up having, you know, an infinite number of possible positions for our solutions to end up when we get to the end of this particular vector. Again, C1 times C1, but it's always going to lie somewhere on these lines. So we're not going to get very far in terms of, like, there was another word you used in there.
Spanned? Line spanned by this vector?
Yeah. So the span of this eigenvector by itself is always or is going to cover, I should say. And only this line. So we have a particular line, y equals mx plus b. I know in one of our previous ones it was very approximately, again, y equals negative 2.2x. And we could, if we use only this particular eigenvector, that's everywhere that we can go. So if our solution doesn't end up lying on this line, we're kind of in trouble. Alright, so what does it mean for a second vector to be linearly independent?
It means that the head doesn't lie on that line.
Ooh, come on, really. My stylus is not always enacting the item that I want it to, so that's cool. Okay, so the second vector is linearly independent if you said the head of the vector does not lie on the same line. Okay, so a couple of caveats to that. Obviously, we're saying that all of our vectors are going to start at 0, 0 anyway. That's where the tail of all vectors are going to start in this particular setup. So what would be a slightly more technical way to say does not lie on the same line?
So this, the full statement is the same as if the vector is not a constant multiple of C, a scalar multiple.
Right? So C2 does not equal what we wrote earlier, sum C1 times C1. Okay. What does that mean for their spans?
Their spans are distinct.
Always?
Yes, they share the origin, but their spans are...
Right.
Oh, I guess... No, yeah. C is... Yes, okay. There's no, like, degenerate C is equal to 0 issue.
Yeah. Right. So, we're going to say that, okay, well, you need to construct some other C2, which is going to go through the origin just the same as C1. And its span, right, all of the possible places that it could land are going to be just some other line. It doesn't even matter what other line it is, as long as it is distinct for all points except the origin itself, which is, again, where all vectors are going to start. So, of course, they're going to share that point. It's just two vectors. So here we have C2, C2, which is going to, again, be represented by all possible locations on this distinct line over here, this set of vectors. So either of these kind of three ways that you want to think about it, that you want to talk about it, that you want to explain it to your teacher who's actually going to be giving you credit for this course, or what have you, as long as my students can explain some version of this, I'll be happy about it. Maybe they can work from one to the next, get the more technical language in there, but the concept is the most important part. You've got to make sure that our two vectors are not actually lying on top of each other or are just constant multiples of each other. Because if we do that, then we're kind of stuck. We're just going to be stuck on this one line forever. But the second that the span of one of the vectors is not the span of the other vector, except, again, at the origin, then we're going to end up with a span of two vectors, two linearly independent vectors. I don't know if this is actually proper notation, but you know what, whatever. Which is going to be equivalent to what?
The whole plane, r squared, or r squared?
Yeah, I sometimes say r squared, but usually just r2. I'm sure Zach has several opinions on that, so... Miss you, Zach.
Love.
post that one for anybody who hasn't met Zach. E to the 2i pi, and Discord and Twitch. Again, most of the time, Zach is also in this class with Stucky and me, and we have a nice little dialogue about things that we picked up through the years on differential equations. Out of curiosity, did you teach DEs at all?
Sort of. We had a combined linear algebra differential equations course. So we're a little bit lighter than the treatment that your outline suggested here.
Yeah, mine's also a very different order from how I taught it. At least the first several times. All right. So I'm going to post this one. Solve the following system of differential equations, and I will also give this in matrix form because that's more fair. But again,
before you go into that, I would love it if you would post the link somewhere so that I can just write things down.
Should be in the chat.
Should be in the chat. It is in the chat. Oh, yeah, makes sense.
Okay. And then just for my own personal whatever, if we want to then check if two, let me just double check because this may actually come later and I'm just forgetting. It's fine. Yeah, okay. It's coming in number 6, so we'll wait on the conclusion on this section. But so we're going to keep in mind all of this span argumentation as we go through, and then we'll take a look at our possible answers for the next several and see if it makes sense.
Okay.
Before we formalize it.
Here we go. Okay. So our plan is, call that A. So first I want the eigenvectors. Well, I guess maybe I would prefer to find the values first. And we could sit here and try to guess eigenvectors.
As fun as that is. Probably would not take you that long, come to think of it.
Yeah, this one...
Once you get a couple of guesses
like
in there.
2-1 maybe, something like that. And then ultimately the goal is that we want xy is equal to c1 c1 e to the lambda 1t plus c2 lambda 2t. So okay, that's the plan. Yeah, I'm gonna look at stream real quick. Okay. We'll go down. So for part 1, I want to take the determinant of a minus lambda I, so it's going to leave the off-diagonal entries alone. Or I think I said it the other way, but I'm going to do this.
Sounds good to me.
And we'll set that equal to 0, but we'll compute it first. So that's going to be 3. Okay, just this once. And then minus 1, which is 3 minus 4 lambda plus lambda squared plus 1. Oh, I see something nice here. Let me just do that right away. 2 minus lambda squared. I don't know why I felt like writing it like that. And I want to set that equal to 0. Let me just make sure I like that. I don't think I got any signs wrong, so take it. Okay, so we only get one eigenvalue, which is potentially concerning, but not necessarily. Lambda is equal to, yeah. Okay. I guess this is concerning enough, I think, that it's going to screw up step 3, but we'll get there. So this means, so I'm going to plug lambda equals 2 in there.
Your teacher put something in that foiled everything they just said.
Minus 1, 1, and look at that. So this is equivalent to 1, 1, 0, 0. And so that means that equal to 1, negative 1. That looks good.
Yeah, how are you getting that last step to say this is what C is?
I'm saying that, I guess I'm not being super kosher in the linear algebra sense. I'll bow to Gauss Jordan here for a sec.
I don't care which way it is. That's fine.
Yeah, but it's like is that a free variable? Well, so okay, this is a free variable, because that's the only pivot entry, and so this so I'll go and set the free variables one at a time to be equal to 1, and then see what that implies, right? So in this system, this top equation says, a plus b equal to 0, and b is equal to 1 is my assumption here. So a is equal to negative 1.
Right. So whichever way you want to do it, that's perfectly fine. We already discussed last time, since it's a constant multiple out front, you could just choose a different b or choose a different a, and whichever way you want, as long as it's a constant multiple of negative 1, 1, then we're all good. Yeah, so I actually have 1, negative 1 in my notes, but again, none of that matters.
Hi, Penn Center!
Hey, Penn. How's it going? Eigenvalues, absolutely. Even eigenvectors, if you believe it. Okay, so now that we have an eigenvalue of 2 and an eigenvector of negative 1, 1, what do we do with that?
Well, I certainly believe that, let's move I certainly believe that, since the whole point of what I wrote down in 3 is that it's a linear combination of two independent elements, I don't have a second independent element, but I believe that the linear combination of the 1 independent element is going to be good. So we'll start there.
Okay. So absolutely, we have one element that we can plug in for C1 and lambda 1, which is definitely going to work for us.
Right.
Step 4 profit. So yeah, obviously this is not going to work in terms of like if we just let it be plus C2 negative 1 1 e to the 2t.
Right.
We're just going to have two constants that we add together to form a single new constant. So, right, that's obviously not going to work.
Right.
That'll mean that we only have one independent value that we can get for all of this, and then therefore we have to lie only on the line given by the vector negative 1 1, which is very boring. So our system is much more robust than that. You can pick numbers that are not on the point or along the line matching the vector negative 1 1, and you'll get something. So clearly this is incomplete. We still need to go out there and say, well, how should this then be able to cover the entire span of R2? And we already discussed that in order to do that, we need a second eigenvector, which is going to be linearly independent. So how do we do that if we've only got one?
I don't know. I mean, yeah, like we can pick almost any vector I want, and but like I don't know what to do with it. Like
99 negative 2 looks tasty, yeah.
Sure does.
So when we were back on this step here with our solving for the first eigenvector, what was it that you were assuming that you didn't write?
Sorry, when we were where? Oh, when
Sorry,
we were there.
part
Okay.
2.
Right. So, okay. This blue matrix is equal to A minus 2i. And I'm setting that
Right. So it's not like it's wrong or anything, but typically what I have my students do anyway is to say, okay, we're going to augment this with what's supposed to be on the other side. So in this case, we have both of those things, 0 and 0. We're doing this, that's not really a transformation, but we're doing our a minus lambda I times arc C should get us the 0 vector in order to make sure that our a times c is going to get us the same thing as lambda times c, right? That we get this steady state vector that we've been looking for the whole time. So we get the steady state vector. You already figured it out. It's negative 1, 1. Again, if we if we set this over here and say, okay, we're augmenting all this stuff with 0, 0, nothing changes. But this does tend to lend itself a little bit better to come up with that equation, because essentially you're just reading it. And, you know, to everybody else in the audience, clearly Stuckey knows what they're doing here, in terms of making sure that all of these equations are represented and then legible and then useful. Right. So we find the particular A and B that we want to make this particular eigenvector show up. So then we say, well, if we do this again, obviously we're going to get the exact same result, and it's not linearly independent. And Penn is absolutely right. As long as we pick literally any other variable, or sorry, any other vector, it absolutely doesn't matter what we pick. However, there is a perhaps, like, you know, the slightly better way to do things that some people will insist on. I really don't, because it doesn't matter any, but what I have my students do is say, okay, so this produced a particular steady state vector. What if we assume that this eigenvector is itself going to be the result that we get? Back here. So instead of a minus 2i, in this case, times ab getting us the 0 vector, what if a minus 2i times our first eigenvector gets us our times our second eigenvector gets us our first eigenvector? So that will at least guarantee what? Yeah, I can't do that one here. Hang on. Not let. Let's replace. Right, so what are that? Aw, Lo, thank you very much. I am, in fact, almost 42.
You gonna have a birthday stream?
I don't know if I'm going to announce the exact day, but you know.
Fair enough.
We'll call it at some point during the week. Probably that same Friday, whatever it is. Because that's our party day, so, you know.
True.
But it is late September, so that's going to be Friday the 27th, I think is probably going to be our birthday celebration stream. And we're going to have to find our copy of Hitchhiker's Guide to the Galaxy. There it is. Because this is 42 this year, so...
Exactly.
I've got all my pages dog-eared. Read random quotes. Okay. So if we replace the 0 vector with xi1, and this time say that we're looking for xi2, what is that going to guarantee?
So I suspect, based on the tone of this conversation, that the answer is that's going to not be a constant multiple of xi1. Now, I'm not entirely sure I see that, but I guess if it were xi1, just like, let's pretend straight up it's exactly the same. Yes, because if it were xi1, then it would be equal to 0, since that was the whole point of xi1. But since xi1 is not 0, we're going to get something else.
Right, and if... let's see, we got specifically -1, 1 here. Times a particular xi2. The curses. We're trying to figure out, right, which... Let's reverse this back to what we had originally. Then... Come on. We're playing games, apparently. So if we expanded this out, right, this would be a xi2 is equal to a lambda I plus xi1. So we're... Go ahead.
What?
Sorry, there's a xi2 in there. Sorry.
Okay.
100%. Right, and then I times xi2 just gets us lambda xi2. Right, so in this particular case, what we're saying is there's going to be a secondary relationship that exists, that a times xi2 is not just going to get us lambda xi2, because there's only one vector that's going to do that, it's xi1. But now what we're going to do is we're going to say that it's going to get us the same thing plus our original xi1 vector. So that now there's going to be a separate and distinct xi2 which will do that. So it forces linear independence on this particular relationship. Now I think I can probably prove that later on when we talk about how to show linear independence of two particular vectors. So for right now, I'm probably going to leave it like that, which is maybe unsatisfying. I recognize that's an option. But let's work with this in practice and see what happens. Alright, so Stuka, do you want to take it from here?
You want to see that computation for this example?
Yep.
Okay. Sure. All right.
Right, not the exact thing I did, just the let's replace 0, 0 up above with our C1, which was negative 1, 1.
Okay.
And my favorite math subjects, probably differential equations, which is one of the reasons that I opted to teach this. I also took the original undergraduate differential equations in my sophomore year. I took it as a refresher to get into my master's program, which was a compressed course of multivariate calculus, differential equations, and linear algebra all at once in one semester. It was abbreviated because they assumed that we knew what we were doing anyway. And then I took the graduate level ordinary differential equations class, which was pretty much the same thing as our undergraduate ordinary differential equations class, plus a couple of extra topics at the end. And then I took both partial and nonlinear differential equations as part of my master's. So we had to do a 2-course series, and that was my choice, as opposed to stochastic systems, which could have been cool, but I didn't really understand linear algebra anywhere near as well as I do now, and statistics, which I said, yeah, no. I took calculus statistics as one class at the beginning of my master's. That was enough for me. All right. Now what?
Well, so yes. I mean, we can play the same game, yeah. So if we say, okay, that's a free variable, then b is equal to 1, and so a plus b is equal to 1. So a is equal to 0. And so let's see, 2, got a little fancy there, is 0, 1.
So I agree, having a... Thank you, Ben. Dynamical systems and chaos theory, not really that much. I was much more motivated at the time by, well, I mean, trying to get a teaching position, but that's not the point. I was much more motivated by, like, number theorying, using differential equations to do some cool stuff with machine learning, but that was actually my second job offer. Was I was given an offer to work on a fraud detection team as part of an insurance company. So could have been cool, could have been interesting. Probably would have done machine learning and all sorts of cool stuff. So would have been interesting, but yeah, teaching was my #1 passion. So okay, so we get 0, 1, and what does that do for us?
I don't know.
Thanks, Peach Tea. Okay, so at this point, this would still get us something that is linearly independent, but it's still a little awkward due to the fact that we'd have, you know, C1, -1, 1, e to the 2t, plus C2, 0, 1, e to the 2t. I mean, realistically, right, we could still combine a whole bunch of this stuff into here and say, like, well, this is just going to be like 1 plus C2 in that second position.
Right.
So it's sort of looking like it's linearly independent, but at the same time, it's got the same e to the 2t part. So it's going to be a little awkward in terms of like what that actually is going to look for us. What that's going to look like for us. There we go. So back when you said this is going to be a free variable, one of the things that we have typically encouraged our students to do is to say, you know what, let's have it not just be a quote-unquote free variable and let it be like a single value, but what if b was just a free variable? So if our b were equal to t instead, then what would that end up doing for us in our equation?
Or the other way.
Yeah, I almost just accepted it anyway. But absolutely, right? It's going to end up being, right, a plus t is equal to 1 as our first equation, and then we solve for a, so a is just going to be 1 minus t as what you have here. If you separate that out into two pieces, what do we get?
So we're gonna get a piece that depends on t and a piece that doesn't.
And what do we notice about this?
Well, I noticed that the t bit is, or the vector next to the t is the first eigenvalue.
Yep. So if we were to, write this all out in an expanded form with both of the pieces, what do we end up getting?
So let me put this up first because I know what to do with it. Call that C2. And then and I'd like that to look a little nicer. So yeah, okay, we can do something. C2T plus C1.
Brandon, haven't given it two thoughts. Yeah, the U.S. economic market at this point, I've heard, is turning extremely volatile, which it is ultimately not going to affect me, really. All of my stuff's going to stay in the market, and it'll get smacked around. It'll still continue to grow exponentially, because that's compound interest for you. And hopefully none of my accounts will completely get folded, but at the same time, they're pretty long-term, decent yield investments. So I don't think that the U.S. volatility of the market is going to affect me all that much, honestly. Nowhere near as much as it slammed my parents when 2008 came around. Whoa.
Yeah.
Okay. So we've got all these little bits. What are going to be the, actual linearly independent pieces?
Like 1, 0 and negative 1, 1.
No, not really, because those are just constants.
What? Those are.
So, I mean, yeah, they're vectors, right? But at the same time, if we're talking about two unique pieces to our solution, maybe I'm thinking about it from the wrong perspective, but so I guess there's two ways to look at it. One is we're looking at our, what is going on with this thing? It's like picking a random tool to work with instead of the one I selected. So one is to say, okay, well, we've got our eigenvectors, which are going to get us two unique directions to look at. And so we've got our -1, 1 is going to be this direction here, and 1, 0 is going to be this direction here. Times constants. All right, there's also another way to sort of look at this, and that is, what are the unique functions that we're going to be dealing with if all of this were to be multiplied out?
So the exponential e to the 2t, and then t to the 2t.
Yep. So for these two things, these are going... Oh my god. Oh, you know what? That's the problem. It's trying to click stuff on... That's bizarre. It's trying to click stuff on the window behind Excalidraw. And it keeps changing my icon to match whatever it is on the complete opposite window. Alright, anyway, we're better now. So anyway, these are going to be the linearly independent functions. Which are going to operate in the background. And when we start talking about second-order differential equations, this is actually going to take a much more prominent role in that we're going to care much more about functions than we are about eigenvalues and eigenvectors. In traditional differential equations classes, we actually start with second-order differential equations, and then first-order systems is like way at the end, and how you connect how you connect all this stuff you've been doing with second order systems or second order differential equations to, like, now let's use matrices to get all that linear algebra together. Pavel Grinfeld, the like major proponent of what I'm doing here, said that if instead we teach this the other way around, where we start with first order differential equations, we work into first order systems, then we get all of the sort of background knowledge we need for linear algebra in a much more approachable setting, and it doesn't feel like it's completely independent and, you know, disconnected from all the other topics. So I don't know if you have any opinions on that, Stucky.
I don't know.
Or we just haven't done enough of it yet anyway.
I mean, aesthetically, I like the principle of keeping everything first order for as long as possible. But I've never really felt great about motivating this, the cases outside. Well, specifically this case, the repeated efficient systems.
Yeah, for me it was always, well, we just need to accelerate the polynomial that is attached to this particular function.
Right, and I think it's fairly, maybe this is a argument for the orthodoxy. I think that in a way that you could very much do, but feels a little bit more vertigo-inducing. There's this argument about like recurrence when you differentiate t times e to the 2t
Mm-hmm.
that produces itself as well as these like lower order terms, right?
Yep.
And in the second order setting, you can sort of see like, okay, well, I want these things to all collapse onto each other. Again, I'm sure you could do that here, but I've never seen it done. And perhaps that's the only reason why I find it like a little disquieting.
I mean, it definitely is a little bit odd, and we could do that. We certainly could say like, okay, what is xy prime, and let's actually figure it out. So again, we could go back. Actually, I did this at the end of last class after everybody ducked out. I said, okay, now let's actually show what happens when we plug this in. And I said, okay, let's take our a from above, which 1, -1, 1, 3. Right. So let's take our transformation matrix, and let's now plug in x as the top row of all this stuff and y as the bottom row of all this stuff, and then show that both just taking the derivative on the left-hand side. I pointed to my right. Taking the derivative on the left-hand side and multiplying by our transformation matrix are then going to get us the exact same thing in both places. So it was a bit, yeah, it can get tedious. In this case, it's not actually terrible. It's just going to be a little bit different.
Sure.
Right, and we're going to see, as you said, in this particular case, our t e to the 2t is going to get us 2 terms as its derivative. So, sure, we take the derivative of t, it just becomes e to the 2t, and then we take the derivative of e to the 2t, and now it's 2t e to the 2t. And then, constants and everything else all are still knocking around in there, so we got to figure out what's going to happen. But one thing that we can see immediately is that when we take the derivative of c2t times -1 e to the 2t, then the first term where we take the derivative of t, that's going to then get us the exact same thing, only negative, as c2 1 e to the 2t, taking that derivative and the 2 getting knocked down. So I think that there might be some motivation in just saying that, like, that's going to happen automatically when you take the derivative of x, the top row.
Sure.
All right, so let's see. At this point, we're going to have, from either of those perspectives, again, either we have linearly independent eigenvectors, and now we've got this t term, which is going to help make sure that all of the terms end up in the right place, and when we take derivatives, all the right terms cancel out. Or we could look at it from linearly independent functions, e to the 2t and t e to the 2t, which are then going to be, because they're linearly independent functions, we now have two separate function types which are going to be acting on this differential equation. Again, there's a connection here. It's going to be important. We'll show more about it a bit later. Again, apologies if that's unsatisfying. Do you want to add anything else?
I don't think so.
Alrighty. So let's go back up and just to the right. 3. No, that's what we just did. 4. Yeah, I mean we just discussed this. So, what's the issue with the above system's solution? Right? We just said, well, they're not. The solutions we got are not linearly independent, so therefore we had to do all this extra stuff here. Here. Pop that in there. 100% works fine.
Yeah.
Okay, let's take number 5 here. Solve the following system of differential equations. Again, I will rewrite as a matrix system.
Alright. Let's go. Minus 3 minus lambda 5 minus 2 minus 1 minus. The determinant of that is we're going to get lambda squared. We're going to get plus lambda and plus 3 lambda. We're going to get plus 3. And then we're going to get minus negative 10. Set that equal to 0. So our lambdas are going to be 2 plus 1 is 4 plus 13. Just checking that determinant real quick. Everything in sight is negative, so yeah, I was expecting to see positive terms, positive contributions to that linear term. Yeah, okay.
How'd you get the part under the square root?
So yeah, if yeah, this is this is just this annoying trick, right? Where you can pull out the 4.
Sorry. You're saying that's 2b prime?
Yeah. Sorry, yeah. Right, when the middle term is even, then you can just use the quadratic, but you don't need the denominator, and you don't need the 4 in the square root. So you can pull out a factor of 2, right? And it's just
Okay, with one minor problem.
with one minor problem.
B squared.
Minus. That's good. Oh, well, that's nicer.
For some definition of nicer, yeah.
Okay.
I will agree with that lambda.
And then, so I'm going to pick lambda 1, and which am I going to pick? I'm subtracting lambdas, so I want as many negatives as possible. And then we're going to plug that in. This is minus 1 plus 3i. This is 1 plus 3i. Good. This is minus 2, 5. And that's going to go to... prefer not to. So then C1 is...
with a negative 2, I believe.
With a negative 2. Okay.
Yep. So, again, anybody who is not used to some of this other stuff, again, we're just saying that this is going to be, excuse me. No, you know what, this part. Here we're saying that we have a negative 1 plus 3i multiplied by C1 minus 2C2 is going to be equal to 0, so then this is going to be equal to 2C2 and so therefore if the values of C1 and C2 respectively are the opposite coefficients, then we get a solution. So again, we don't really care which solution it is as long as it is along the same vector. So in this particular case, 2 negative 1 plus 3i is going to be perfect. Right, and there was a bit of an assumption, the first one, in that, yeah, sure, these are going to end up being linearly dependent because 5 and 1 plus 3i are going to be multiples of the other things up above, which is true, but yeah, you probably want to show it if you're doing this for the first couple of times.
Fortunately, I have you to tell me that I got my lambda right, so I took advantage of that.
That's true. Yeah, I'm also sitting on an entire page of this problem worked out tediously step by step, so I can see precisely where everything is. Okay, so we got that, and right, I end up having the I don't want to say opposite, but, you know, basically I did the opposite operations and did a complex conjugate of what you have, which ends up getting me -1 plus 3i 5 as mine. If you were to multiply this by -1 minus 3i, you should end up with the exact same thing. That doesn't sound right.
Maybe divide by 2.
Yeah, divide by 2. Something like that.
Something like that.
At any rate, so yeah, once you get all of the stuff in the proper locations, then it's going to actually work out for us. Okay, so that is Xi1. How do we get Xi2?
Well, the same way. But because the only thing that's going to change here is that you have a plus sign there. That means that this minus 3i. Alright, yeah, that's a good idea.
Something like that. At least, you know, most of it's going to be the same, so.
Yeah. Yeah, good. Yes.
Yep, so same deal. We're going to move the 2 to the opposite side to make it 2 Xi2 is equal to you know what? That I should not have written that up above here. Sorry. That was not Xi1 and Xi2. It's just like
right.
x1, x2, or xy, or however we want to state it.
Right.
It doesn't actually matter, right, how we're doing it. We're just saying these are the elements of Xi1. All right, redefine. It works fine. But again, either way, we end up just having the imaginary portion of this, switching its sign. It's going to be the exact same values, but then complex conjugate of the other one. Alrighty, now what?
Proceed. The general solution. As usual. Hey, buddy. So,
Yep.
minus 2 plus 3i. Okay. And
With one minor change.
Is there? Minus 2 plus 3i. That's the correct eigenvalue.
Those are the correct eigenvalues.
They are attached to the eigenvectors I was trying to attach them to.
Yep. E to the lambda.
T.
Yeah. All right, now without being too pedantic here, there's another way that we could express all of this stuff, because, wow, we've got like a lot of stuff going on in here.
Right.
With the fact that we have all these eyes comes the fact that this is no longer going to be something in the real number system. And so we look at it and say, okay, well, clearly that's not okay. We want something that's actually a real number. Right? It has to be defined in the real numbers for any xy that we pick. So as it stands, that's going to be a bit of a problem, but how can we remedy the situation?
Euler?
Yeah. So at least taking one step in the right direction, we're going to say, okay, this is going to be e to the negative 2t times e to the negative 3it. And then same thing over here. And our vectors are also going to split up. Into 0, negative 3i like that. And 2, negative 1 like that. And same deal over here, but with 0, 0, and positive 3i. Alright, still linear combinations, still all that stuff. Cool. E to the negative 2t is just going to stay like it is. We like that. It's cool. But this one here is going to be a little bit of a problem because we don't like it as is. So, as you said, we're going to use Euler's formula to break this down. My suggestion is, of course, that we're going to say this is e to the I times negative 3t, and keep that as like a variable piece. So, e to the I theta, as we know, is going to be what?
Cosine theta plus I sine theta.
Negative. Alright, now I will spare our dear viewers the pedantic algebra that goes on from here. However, suffice it to say, right, we're going to get something that is fairly large, fairly ugly, fairly involved, but at the same time absolutely 100% necessary. If we want to see this again after stream, I will go through every logical step to everybody's satisfaction. But for the moment, I think we could probably say, hey, look, we've got two major behaviors that are going on here. We've got some e to the negative 2t times a cosine, and an e to the negative 2t times an I sine. And with that, we're going to get several major behaviors which we can then group together. So let's see. So what is going to happen is that we're going to eventually get that we have a top row within these first terms here. We're going to have a top row which has real terms, cosine of 3t. The negative, we could just say, all right, well, that's going to, since cosine's an even function, it doesn't matter whether it's doesn't matter whether it's positive or negative. This is going to just be the same as cosine of 3t instead of cosine of negative 3t. For sine's an odd function, so that's going to stick a negative out front. But for the real component, we're not going to have any because this is an imaginary component and there's nothing to change our imaginary into a real component. So we're going to drop this for the moment. For the lower, we're going to have a negative 1 times cosine of 3t. And we're also going to have our I, in this particular case, multiplying together to get us a negative 3, which then, again, is going to be changed around to a positive 3 due to the negative coming out of the sine function. So plus 3 sine of 3t. Okay, and then from the second group, oops. For the top stuff, we're going to have exactly the same items. So this is going to be another 2 cosine of 3t. But the constant out front is going to be a C2 instead. And then on the bottom, right, we're going to have a negative 1 cosine of 3t. And then here we have a negative 3 times a negative 1 gets us a positive 3 again. Sine of 3t. So when we go looking for the real numbers, all that we've got now is this C1 plus C2 times all that stuff. 2 cosine of 3t, and then negative 1 cosine of 3t plus 3 sine of 3t. Okay. Then, what we're going to do is we're going to look for all of the imaginary stuff. And I left out e to the negative 2t here. Sorry. It's just multiplied to everything, so I'm just kind of pretending. It'll be attached to everything. Right. So when we go through and look for pure imaginary stuff, we've got here, this 2 is going to be multiplied by our I sign. And that negative is coming out. So we get a negative 2 sine of 3t. God, come on. And that is multiplied by c1. And on the bottom, again, pure imaginary stuff, we have a negative 1 times our I sign. The negative's coming out again, so that's going to be 1 sine of 3t. And then we also have a 3i times our cosine of 3t. Oops. Oops. Right, we already took out the I, so we don't have to worry about that. Okay, and then plus C2 times, and we do the same thing for the second group. Up top, pure imaginary, we just have the sine of 3t. So 2, come on. And then down bottom, we have a pure imaginary negative 1 sine of 3t and a negative 3 cosine of 3t. Okay, which again can be simplified down to the bottom by saying, well, our I is already factored out. And again, these two vectors are the same as each other, but they're off by a factor this time of -1. So we could just let this be C1 minus C2. And then multiply by our vector, -2 sine of 3t, 1 sine of 3t plus 3 cosine of 3t. Oops. Okay, and then end all that, because everything has e to the negative 2t attached to it. Alright. So, next question. Did I lose anybody? Yeah, color coding is definitely key when you start getting into like... How you doing, Dr. Gold?
Hey.
Yeah, so PhD, it's very important at this point. We're looking at this and we're saying these terms aren't actually disappearing either, right? Because it's a C1 times all this stuff minus a C2 times all this same stuff. So everything kind of collapsed into this at least more compact form, but it's not like just literally disappearing. Now here's the part you're probably going to hate. What we do with this is we say, okay, we've got this e to the negative 2t bit times. We're going to say that the first constant, c1 plus c2, is just a new constant, c1 star. Right? I do this all the time. My students hate me for it. It's fine. It doesn't matter. But we're just going to assume... you know what? Let's use a different color this time to highlight the fact that we're going to let C1 plus C2 equal C1 star, which is going to belong to the real numbers. Now, this is important because we're dealing with imaginary numbers as well. So we're going to say that just C1 plus C2 is going to belong to the real numbers. Now here's the part you're really going to hate. Let C1 minus C2 be equal to C2 star and, well, okay. Let C1 minus C2 be equal to... I guess technically we could call it... Hang on. You know what I'm trying to do. Negative I C2 star. There's a reason for everything. So what's going to happen here is we're going to get this plus I, which multiplies to this negative I, or negative I being I to the third, multiplied by another I, we just get I to the fourth. So now it's just 1 times C2 star. Which now, all of our constants are real. Renormalizing constants. You're cool with this? Okay, that's good. And anybody who doesn't know Dr. Gold, at Actual Education, I think you got more SAT prep tonight. Is that what you got going on? All right, and then we just copy over the same stuff we had from before. So this is going to be 2 cosine 3t negative cosine 3t, and you know what? We're just going to put the 1 in there because why not? And I ran out of room already, so yay. Alright, so next question. Does anyone hate it?
What say you, chat? But no, seriously, not really. That probably doesn't surprise you. Yeah.
Yeah, I mean, somebody who's in the class, right? And has known this for a while. Does not surprise me that you're okay with it. I don't not hate it, but I understand not hating it. Alright, fair enough. Okay, and then if we really want to go one further on this, we can take all of our cosines and all of our sines, and we could potentially regroup them, or say like, you know, we're gonna have you know what? Let's just leave it. Right, there is the possibility that you could also break this up from here and say, I'm going to separate this into its two constituent parts, cosines and sines, and then combine eigenvalues, eigenvectors as necessary to get it to all work out. Let's see. Nah, that's how I left my other answer too. I'm good. I was thinking for a minute, oh, we've just got like, you know, we're just making a eigenvector times cosine plus an eigenvector times sine, but that's not this one. There are other times where you will rather easily get that, but I think the problem here was we had maybe that's just imaginary, like just the pure imaginary solutions. Okay, so the big takeaway for all of this is that this is this x, y that we have for this particular one is a real valued set of solutions. So again, this is making sure that all of our values, no matter what t, no matter what x and y we plug in, right, we're always going to be able to figure out some location on our xy plane as a function of t that is going to then consistently move along with the exact phase plane that we see when we look at the original problem way up here, right, as our transformation matrix -3, -2, 5, -1 has no imaginary components in it. So all real values x, y are going to produce some sort of, you know, phase plane vector x prime, y prime, which is going to tell us the direction in which it's going to go from that particular point and how fast. Okay. So now the last question comes in finally, where, yeah, let's just bring that back up to the top. So how can we argue for existence and uniqueness for all of these solutions, for the solutions of systems of differential equations? And Stuki, if you have anything to say about the previous, let me know.
Yeah, not
Or
really.
just go for it. Which, also fair. Okay, so how do we argue that solutions are going to exist for all of these systems of differential equations?
Beyond the argument that we have these three types of systems, we really these really are the three types of systems, because you can make this claim from the characteristic polynomial, and then we know what to do, right? we know what to write down, sort of.
Right, and what was the major concern when we were just looking at first order systems, or first order differential equations back before this? What was the issue with the potential existence of a solution?
I don't really remember. I mean, you can be nervous that the function is not differentiable at a particular point. You just sort of back yourself into a corner.
Right. So if something's not differentiable, that's going to be a problem. And in this case, what we saw is that what is going to be not differentiable?
It doesn't feel like there's much. We've got exponentials, which are fine. Yeah, I think everything is differentiable.
Although we do have a slight problem somewhere.
I mean, at the origin?
Yeah. So
I don't have a problem with the origin.
Well, I mean, it's a point where we were looking at some of the examples from earlier, and they were throwing errors. So we were trying to say, well, how are we going to be able to move if we're at the origin? And the answer is you don't move, right? If you're at the origin, you just stay where you are. So I guess it's not really non-differentiable. It's just that it's it's not singular either, is it?
Yeah.
Right, so in every single case, we can plug in 0, 0 for our x vector, and our x prime vector is also going to be 0, 0. So we're just not moving, right? It's going to be considered a equilibrium point. And so therefore, and the other problem is that it's for all systems of this particular type. So 0, 0, x bar equals 0, 0. Will always return x prime equals 0, 0. So this is the only issue that we're ever going to have in terms of the existence of a solution anywhere in the entire R2 plane. Okay. What about the uniqueness of solutions? How do we know that the solution that we find is the only possible solution?
Well, again, for these solution types that we've written down, we have I mean, you pick your favorite starting point, and you want to say that it's the system of two equations and two constants, and so, well, we don't have a uniqueness problem, maybe, or so we don't have an existence problem, maybe, but we definitely don't have a uniqueness problem. Wait, hold on. Is this the right thing to say? So
So there's a process that we went through. And what was it that we actually found?
we found a general solution.
Also true. What was that general solution made up of?
It's a linear combination of two solutions.
And linear algebra wise?
Independent solution.
Right, so we found a set of linearly independent. What would you call those things? I mean, they were eigenvectors, obviously, but in terms of linear algebra, what do you call those eigenvectors when, you know, as a pair, they then span the entire R2 plane?
The vectors certainly form an eigenbasis of R2.
Right, and that was really the key word there, was our basis vectors. Anybody who knows anything about linear algebra, right, this is saying that if we find these particular linearly independent vectors, then we could, again, span, we can get any value we want in the entire R2 plane. Does that mean that they are literally unique?
No.
But what does it mean?
Um, it means that when you set t is equal to 0, then you have you have a linear combination of two basis vectors, which is equal to your starting point. And so there's a unique solution. There's a unique linear combination that will get you to that starting point.
Trying to figure out how to translate that into what I am thinking in my head, but I don't, yeah. I could just be wrong. It's fine. So, yeah, we found a set of linearly independent basis vectors, which, if we were to say, like, oh, well, that's not a unique solution, well, keep in mind how we found this, right? Our basis vectors are based on our eigenvectors, which are our steady-state vectors from the first-order differential system that we have. So, if we found different basis vectors, you know, anybody else, right? Anybody else can find different basis vectors if they just plugged in different numbers into their eigenvector part. your step
Right.
2 that you found from earlier. If they just plugged in a different number, they get different basis vectors, but they're not really different, right?
Well, I mean, the I mean the general solution is not different. They produce.
Arg. And again, this could be different for every single person that we like assign to here. Go find a set of basis vectors for us, right? But every single one will always end up being some constant times xc1. You know, some xc1 or your xc1 versus their xc1, and c2 times whichever other xc2 we're using. Now, there isn't, like, you know, a gold standard for finding xc1 and xc2. You don't have to, like, normalize it, although, honestly, right, that's probably the best way to compare everybody's. If we're going to, like, I don't know, if we're going to do this in, like, a technical sense. You know, take everybody's across the room, normalize it, and then are they the same, or are they just literally the opposite? And that's good enough. So, right, everybody's going to find the same basis vectors slash a constant multiple of each other's. So, in a way, right, this is a unique set of solutions. It's just that they're going to be constant multiples of each other if we're looking for those particular vectors. But yeah, everybody ends up with the same general solution, just with a few constants that are off, and that'll be all right. Do you want to make any arguments against that?
I mean, I'm not so convinced that this is the case in the repeated root setting. It still doesn't matter. You still get the same general solution, but I think C2 could be quite bizarre. Right? I mean, if you don't insist on having a Jordan block, right?
Oh, yeah, that is a Jordanian. Okay. Yeah, if you don't insist on particularly finding it in the same way that I did it, then yes, you could, in theory, have a different vector, literally different vector, which then still gets you the same result in the end. It's just going to be a little bit different.
Mm-hmm.
And if anybody else out there wants to argue, feel free. So let's drop a question here in the repeated case. R. Which, as you said, it seems like definitely should be. But perhaps this is the only problem that we're going to find, is that it's just the repeated root case is not going to have a unique solution, but at the same time, you're going to get the same result in the end, so, like, is it really going to matter?
Right.
We also do tend to see this in even first-order systems and stuff. Well, I guess not first-order, because those are uniquely defined. Arg. Leibniz was able to prove that here you're going to get solutions by doing this. In theory, there is an idea that there could be some other function out there, which we just can't come up with through any easy means, that is also the solution to the given differential equation. You know, it could just be like a random higher degree polynomial, that not literally, but there could be some other function out there which works for this that is not found through the exact same method that we're using. But most of the time that ends up just being kind of theoretical. And it's like, how would you even go about finding a solution for this unless you just were given, hey, by the way, this is a solution to this following differential equation. That happens a lot with, like, nonlinear stuff, especially. A few of the examples in the Trench book that were at the very, very beginning of the course that said, is this a solution to the following differential equation? Several of the nonlinear examples there, like, you could have a very simple solution, but also you could potentially have a very complicated solution, and they would not be found through the same means, through the same methods. So it's very strange when you start getting into all sorts of big stuff like that. Right, okay. So this is going to define, kind of as a pseudo wrap-up here, this is going to define what is called a fundamental set. of solutions. And in order to find a fundamental set of solutions, well, we went through the process of finding the fundamental set of solutions, but there is a way to check whether or not something is a fundamental set of solutions for the given system of equations. So, what we're looking for is do the given solutions form, yes, a fundamental set, but form a linearly independent set. So the test for this is what's called our, come on now, I should probably just leave it as an accent. Yeah, that's fine. Is a W matrix, also known by the formal name Wronskian. And this was discovered by Polish mathematician Wronski. Sometimes I think spelled with a Y, but same deal. What we want to do is to find the determinant of the concatenated solutions as vectors. So we're going to take our x1 vector, concatenate it with x2 vector, ... all the way out through xn vector. And find the determinant of that set. And if the Wronskian of that fundamental set of solutions is not equal to 0, then we have a linearly independent set of solutions, and therefore they form a fundamental set. So coming from earlier, one of our examples we had that x1 was going to be negative e to the 2t and e to the 2t. And x2, so for this you can see what we're doing is we're taking all of the bits that belong in this. So our fundamental set is our eigenvector times e to the lambda 1t. And then this is just getting mushed into one single vector. And x2 was equal to, we had a, is it 0, 1? Curses. Yeah, C2T. Okay. So if I rewrite this as a vector system, this was going to be e to the 2t up top minus te to the 2t bottom, we had 0 e to the 2t plus it's different than my notes, curses. Okay, oops. No, that'll work. Okay. Okay. So we had our two separate pieces, one of which was going to be e to the 2t 0, and the other one was a negative t e to the 2t minus e to the 2t. So that needs to be also minus. And then at the bottom, it was the positive version of the same. Okay. So what we're going to do is we're going to take these and then form our fundamental set. Or put it into the Wronskian and test whether this is the fundamental set. So e to the 2t 0 followed by negative 1, 1 of e to the 2t plus t e to the 2t. Come on. Probably should have zoomed out. It's fine. Okay. 2t and 0. This was negative e to the 2t minus t e to the 2t with a positive version of the same. So the Wronskian for this, we need to find the determinant of e to the 2t with 0 underneath it. And then over here, negative e to the 2t minus t e to the 2t. And e to the 2t plus t e to the 2t underneath it. Now, in this particular case, I think everybody, if you see where this is going, right, this one is clearly going to work. We have a 0 as one of our elements in the set. So unless this managed to multiply stuff perfectly such that all the rest of the terms somehow canceled out, then yeah, this is going to form a fundamental set. Which of course is not actually going to do that. Right. In this case, we end up with, again, main diagonal. It's going to be e to the 4t plus t e to the 4t minus 0. So this stuff is just going to be e to the 4t times 1 plus t. And this is not always equal to 0, so therefore this is going to be a fundamental set. of solutions. And then we don't have to look any further for any possible other answers. All right. Stucky, questions, objections, clarification?
I am muted. No, I think I'm good.
Alrighty. And if anybody in chat has any questions, wants to clarify something, or completely and utterly smash what I had to say because it was wrong, feel free. Alright, and there's the possibility that I messed up a little bit somewhere in here in terms of like getting the fundamental set of solutions from what we had earlier. I'm not 100% confident in it just because it might have been in a slightly different form than I'm used to and whatever else, but you know, I think it worked. Alright, so finding fundamental sets of solutions, we can again just double check if what we're given is actually a fundamental set, or if it's not, we have to go back to the drawing board and find more. This does get a little bit annoying when you have to, for instance, find whether the solutions we had form a fundamental set of solutions when you start looking at stuff like this. Right, we've got e to the 2t times each of these cosines and sines in each of these locations, and now we have to do the determinant, so now we have to, sorry, other way around from where you're sitting. We have to do the main diagonal, subtract the off diagonal, product of the off diagonal, and yeah, these are going to have to be expanded and then maybe collapsed a little bit because we've got some sine squared and cosine squareds. So it can be a bit frustrating, a bit interesting, but nonetheless, it's valuable in terms of a test to be able to say, is this going to get me an actual fundamental set of solutions, or do I need to go back to the drawing board and find something else? Most of the time, the problem that's actually going to exist is that you don't have this in a form where you can easily see what the eigenvectors are going to be and whether those things are just aligned with each other. So if they're not linearly independent eigenvectors, if you somehow messed it up a little bit, or if we're in the repeated eigenvalue case, right, then we're going to have a problem with trying to find eigenvectors. You got to make sure that those are linearly independent from each other. So that might be the only actual problem where you end up with like an issue to the fundamental set of solutions. But other than that, I think we're in a good place to stop. I will get all this stuff posted to Discord over on Pens. So anybody who might be new.
Great. I'm going to head out, but I want to say thank you for hosting before I do.
Yes, absolutely. Thank you, Stucky, for coming by, and hope to see you on
I'll see you next week sometime.
Monday/whenever.
Monday?
As schedules allow, obviously.
Take care.
Yep, you too. Good to see you again.
Same.
Yeah. No worries, Ben. Yep, that'd do it, definitely. I'm sitting over here at 11:30 at night going, you know, for for 1 second. Why would he be vacuuming at 11:30? So, yep, Penn Center's Discord, for anybody who can actually hear me, is the central repository for a lot of our individual stuff. We also have classes that are coming up and classes that are currently running. Penn Center is running a complex analysis class, and e to the 2I pi, our friend Zach, is going to be running, who is also usually on call with us but couldn't make it tonight, is also going to be running a finite... Oh no. Oh no. Finite functions? No, infinite functions? What? Forgot the name of it now. Of course. Math courses on Twitch. Near future. Here we go. Infinite series. Coming up in September. So anybody who might be interested in doing an infinite series course, e to the 2I pi, Zach, will be doing an infinite series course September through November. I'm going to endeavor to be on it, but it all depends on what time it is. Because I'm now BST, which is UTC +1, I am 7 hours ahead of where Zach is, so it gets to be a bit challenging to find a time that's appropriate for both me and everybody else. So we just kind of let everybody else do their thing, and I'll read on the side. But it also does mean that we can do homework as part of my individual math help classes or whatever it is that I'm doing here on typically Tuesday nights. So I didn't stream this week, just had some other stuff I wanted to work on, so we have been doing just class on Monday and Wednesday for differential equations, and typically I'm going to be doing gaming on Friday. This Friday, however, I will be showing up on Dr. Gold's stream. Again, we're gonna... Let's see. I don't know. Do you have it as Gold? No. Dr. Gold. Is it actual education? Uh-oh. I broke an Enigma bot. Oh no, I broke the bot. Ow. Of course. Streamer. Oh no. Okay. Apparently, I don't have Dr. Gold's listed there, so we'll go with Chad's instead, where I know it is listed. Yep, so last one there. Dr. Gold at Actual Education is going to be hosting an AMA podcast with yours truly, Obi-Wan Pez / N Simplex Pachinko, and we are going to be just talking about how I got to where I am today, some advice that I might have to any students who are out there, all sorts of crazy stuff. So we'll be doing some interesting things like that instead of doing gaming this Friday, which does mean that if I get bored and want to do some gaming, I will just game whenever I feel like it, and maybe I'll stream it as well. So you all are welcome to join on in. Come see us on Dr. Gold's at Actual Education on Friday. It's going to be our standard time, so 2100 BST, which is 2100 back 5 hours is 1600 Eastern and 1300 Pacific. That's in the US. Anybody else who needs that, that's just going to be 8 o'clock, 2000 hours UTC. But we do have it posted in several locations, including both on Dr. Gold's Discord and on Penn Center's Discord. At least I think so. Well, at any rate, it'll be in Dr. Gold's. Yeah, it'll be on Dr. Gold's, where I do not have. Maybe I have access to get a invitation. Boop. All right, so that's Dr. Gold's Discord. It may or may not work as an invitation. Who knows? We'll see. Whee. But at any rate, I will see anybody who is interested on Friday as a part of Dr. Gold's podcast, and we will... I gotta ask him about dual streaming on mine. I don't think that that's something I'm gonna be doing, so we'll just probably be over there. That is in Russian, so I don't think we're gonna go there. I mean that as they're probably speaking Russian. So I don't really understand it. Let's go over to science. Belint is currently starting stream in about 8 minutes. Yeah, it's good enough. Oh, 4 minutes. Much better. So we're going to head over to Belint's and see his stream. It is Home Wednesday, so Belint is going to be working on some art, which is really cool. And I don't know, maybe we'll also work on some art, because why not? Right, so thank you very much, everybody, for coming. We're going to head on over there, and we'll see you again, like I said, either here on next Monday or Wednesday for Differential Equations class. We're going to be talking about further systems of differential equations, including those that are non-homogeneous. And on Tuesday, I think, for more math streaming, for anybody who has any questions, come on and bring those in. And then on this Friday, we'll be doing Dr. Gold's AMA podcast. Next Friday, we'll probably be doing gaming, and then we'll game whenever I feel like it. So I'll see you all later. Thank you very much for coming. My name is Obi-Wan Pez. This is N. Simplex Pachenko. Have a good night.